Okay, looking at chapter 20, the worksheet with solutions. Now we're looking at electric current resistance and Ohm's law. So we have two questions here, two problems. A cylindrical nichrome wire has a radius of 0.200 millimeters and is 5.00 centimeters long. So I have a cylinder. How do I know it's a cylinder? Because it said it had a radius. Okay, so just trying to illustrate where the backside is. I don't know, that's a terrible idea. And we're given the radius and the length. So radius. Oops, only 1 0. So there we have the wire. And the first question we're asked is, what is the resistivity of nichrome? So you just look this up in the table. In chapter 20.3, there is a table that lists a bunch of different metals, and it says that for nichrome, the resistivity is 10 to the minus 6 ohms times meters. Ohms we write with the omega, ohms times meters. And then we have, what's the resistance? Well, resistance is simply calculated. Resistance is equal to the resistivity times the length. My hand obviously hit something there. Divided by the area. So that would be 10 to the minus 6 ohms times meters. There's my, I should have done it in this color. So I have that, and then times the length. So the length was, oh, come on. I just want that to go away. 5.00 times 10 to the minus 2 meters. Notice I converted it into meters. And then divided by the area. The area is pi r squared, so pi times 2.0 times 10 to the minus 4 meters, quantity squared. And when I put that in the calculator, I get that my resistance is equal to 0.398 ohms. Now, for some reason, I only gave you two significant digits there in the radius, so I only have actually two significant digits. So to correct significant digits, that's 0.40 ohms. Now remember, when we do calculations, we're going to keep full digits until we get to the end. Then we'll apply significant digit rules. What will the voltage drop across this wire be if 11 amps of current flows through it? So now we have a current flowing through it. I equals 11 amps. I'm going to redraw this with the normal circuit diagram. We have, there's my resistor. Here's my current going through the resistor. And once I have indicated the direction of my current, I can put the positive side and the negative side, because a resistor resists charge going through. It's going to put a force, if you will, against the charge and thus take away energy when charge goes through it. So the energy drops, the voltage is the potential energy per charge, so the potential energy drops as it goes through, hence positive voltage on the side it started, lower voltage on the side it ended. And Ohm's law has the simple relationship. Voltage difference across the resistor is equal to the current through the resistor times resistance. So that's going to be 11 amps. And now I'm going to use my extra digit there of 0.398 ohms. And that gives me a voltage of 4.38 volts, a voltage drop of 4.38 volts, which, to correct significant digits, is going to be 4.4 volts. And then finally, at what rate does this resistor dissipate power? Remember, power is a rate. I should have said dissipate energy, because I'm asking for the power. And so at what rate does dissipate energy. What is the power? Power is given by the equation P is equal to IV. That is always true. So I could just take my answer there, 11 amps times 4.4 volts. Or if it's a resistor, I can use Ohm's law and say, well, I is V over R. So that's V squared over R. Or V is equal to IR, or I squared R. Any one of those will work. And so I am going to choose the one that has the least potential for rounding error. That is V squared over R. So the power dissipated is V squared over R is equal to, or actually I squared R is the one with the least round off potential. I squared R, which is equal to 11 amps squared, 121 if you will, times 0.398 ohms equals, and that gives me a power of 4.81 watts, or to correct significant digits, 4.8 watts. All right, so that's the first problem. Now we have two problems in this one. So let's just move right on to the next problem. A power supply produces a 10 volt RMS sinusoidal AC voltage. So let's draw what a 10 volt sinusoidal AC voltage looks like. So AC means alternating current. The current goes both directions. I'm gonna use the straight line tool. So there's a straight line. And so my voltage does a sinusoidal variation. And we are asked, number one, what's the average voltage? Now, if you look at this, what's the average of that red line? It's 0. That's why we don't talk about the average voltage for an AC power supply. But then we have, what is the peak voltage produced by this voltage source? So what's this voltage here? By the way, this is V peak and this is minus V peak. And the difference between the two is called V peak to peak. And as I went through in class, the derivation for a sinusoidal voltage is not that hard. In fact, we can do it without calculus. What you do is you first, for RMS, that means root mean squared. And the first thing you do is you square. So if you square this voltage, you're going to have something that is sinusoidal, but with twice the frequency. Okay, I have to ignore the whole thing, so I'm not going to try to fix that. So that is going to V peak squared. Well, what's the average of this? The average of the green, since it's symmetrical but goes from 0 to V peak squared, the average is V peak squared over 2 is equal to the average, the mean, if you will, RMS, the M is mean. So the average of V squared. Well, then the last step, VRMS, the last one is root, the R in RMS. So we square root that, and we have VRMS is equal to the square root of V peak squared over 2. Well, that means that V peak, the square root of V peak squared is V peak. So VRMS is V peak over the square root of 2, which means that the peak voltage is V peak is equal to square root of 2 times VRMS. So all I have to do is put square root of 2 times my RMS voltage of 10.0 volts, and I get 1.41. Oh, not 1.41, 14.1. 1.41 is the square root of 2. Ohm's law still applies for AC current. It does. Ohm's law applies no matter what kind of current you have. At any instant, Ohm's law will be correct. What is the peak power dissipated when this power supply is connected to a 220 ohm resistor? So we're just going to have power is equal to I V is equal to V squared over R is equal to I squared R. The same equation that we used up above. This time around, I'll use the voltage peak and the resistance. So that's equal to the voltage peak squared of 14.1 volt times squared. Now notice, if I square root of 2 times 10 is going to be 2. Square root of 2 squared is 2. Times 10 squared, 100. 2 times 100 is 200. So that's 200 right there. Divided by 220 ohms. So 200 divided by 220 ohms is going to be a value that is slightly less than 1. In fact, it turns out to be 0.909 watts. That's a W. It looks like an N. And I really should have put space here to put that in. All right, so that is our chapter 20 review problems. Sorry for the time it's going to take here. I hid the